All right, so I want to take a couple minutes just to revisit the lesson that we talked about yesterday. We talked about a lot of information, and I don't know if necessarily it was in the best order to help you understand what we were talking about, especially since we were virtual. I don't think that helped anything. So let's take a look at a few things. The title of the lesson today is the fundamental theorem of algebra. Everything that we talk about stems from this theorem and the corollary that goes along with it. We don't focus on, I don't need you to memorize the theorem. Really, the application of it is what we are focused on. So the first thing that you need to get out of today is you'll be able to use the fundamental theorem of algebra to find the number of solutions that a polynomial has. Remember, that was the big focus or that was supposed to be what the big focus of yesterday is how many solutions does a polynomial have, and how do we find what all those solutions are. We tried to preface it by talking about the homework from lesson 4.5, where you had to use our different factoring strategies of chunking, greatest common factor, all that kind of stuff, and you had to find the solutions. And we talked about how if you look at number 1, number 4, and number 5, they all had a degree, I think they all maybe even had a degree of 3, and they all had 3 solutions, or maybe had a degree of 2 and had 2 solutions. Either way, the number of solutions matched what the degree was. And then I asked this question right here. Right, there we go. I said, all right, in 1, 4, and 5, the degree matches the solutions. Why doesn't it match in 2, 3, and 6? And one of you guys said that, hey, maybe in 2, 3, and 6 we have imaginary solutions, so that's why the degree doesn't match. And that was right on. That's a big part of what we're looking at in this lesson, that there are a couple of, I call them counting tricks, or counting irregularities that make it so that maybe at first it doesn't look like our degree matches our number of solutions, but if we count a certain way, then our degree will always match our number of solutions. So here are the 3 counting irregularities. I shouldn't have used this word because I can't really say it, but that's okay. The first one is if we have a touch and go. We know that a touch and go happens if we have something that is to the 2nd power, 4th power, 6th power, anything like that, right? An even power will give us a touch and go. So if we had x minus 2 squared, we also know that that really means x minus 2 times x minus 2. So we would count, really when we're counting solutions, we would count positive 2 as 2 of our solutions. So that is one thing that gives us a counting irregularity. If this were, x minus 2 to the 4th power, then we would have 4 x minus 2's, and then 2 would count as 4 solutions. So that's one thing, again, when we're counting solutions and making sure it matches our degree. That's one thing we need to watch out for, is touch and goes. The second thing we need to watch out for is square roots. When we look at a polynomial, and we're going to look at an example of this in a second, but when we look at a polynomial, if one of the solutions is a square root, it doesn't, it's not like we see a square root here and we can know that, right? As we break it down and as we factor, that's where the square roots start to show up. So one thing that we will find with square roots is that square root solutions always come in pairs. So anytime we have a square root solution, we will always have 2 of them. It'll always be plus and minus the square root of something. The third counting irregularity is complex numbers. Again, when we have a polynomial, we don't see a complex number in the actual polynomial, right? It's not like this is 3i or anything like that. But as we factor it out, then we would see complex numbers start to show up. This will be really clear in the example that we go through here. Complex numbers, because as we factor, because we don't see one right here, complex numbers have to come in pairs. Because you guys know if we have 3i times 3i, 9i squared, and this would simplify just to negative 9. That I squared is negative 1. So our complex numbers have to come in pairs in order for them to not show up in our polynomial. We don't see square roots and complex numbers in polynomials, right? That's what I talked about. But as we factor, they start to show up. We need to know how to account for those when it comes to finding all solutions. Here's that fundamental theorem of algebra that I mentioned, and really what we're talking about comes from the corollary. In the corollary, this first part, if a polynomial of degree n, or if we have a polynomial of degree n, then the equation has exactly n solutions. And then this other part, provided blah, 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 that's just provided the three situations that I just said, those counting irregularities. Now here's the theorem that tells us that imaginary numbers come in pairs. We looked at a theorem in 4.5 that said it was irrational conjugates theorem, and that told us that square roots had to come in pairs. This is telling us the same thing, but with imaginary numbers. That if this exists, a plus bi, or an imaginary number, then a minus bi also has to be a 0. All right, so let's look at a few examples here. Now, as we go through these, obviously they're not going to tell you, hey, watch out for the touch and go, watch out for the square root, watch out for the imaginary numbers. Really, the directions on all of these would be something like this. It would say something like find the zeros of the function by factoring. So when they say find the zeros by factoring, that's really important because under factoring, we have a few things. We could use the GCF, right? That's always our first look. We could unfoil. We could chunk it up. And then we also have our difference, and this doesn't come up too much, but we need to keep in the back of our mind our difference and our sum of two cubes. So when we say factor, here are the 4 things that fall underneath that. Those are the 4 strategies that we have. Now, as a side note, if they did not say to factor, which probably will not happen, especially on a quiz on a test, but just for fun, if they did not say factor, we could look to graph this, right? We know that the zeros, or the solutions to this equation, are the points where our graph either touches or crosses the x-axis. So even if you wanted to use your graph just to double check your solutions, you could always do that. But if the directions did not specify what you needed to do, then you could go to graphing. Lucky for us, our directions say that we need to solve by factoring, so that's what we're going to do. Now, one factoring thing that we need to get a little bit better at and a little bit more used to is if we have a fourth and a squared right here in this trinomial. We can treat this the exact same as we could treat if it was this right here. This and this are almost the same when we look at foiling. The only difference is when we unfoil here, instead of starting with just an x and x, we need to start with an x squared and an x squared. Other than that, we treat them the same. We still think about what can we multiply to get positive 16 and add to get negative 4, or negative 8. The answer would be negative 4. And then we look at these and we say, all right, this is a difference of squares. So we can break it down even further. And now we would write this in the simplest form. And then, again, our goal is to find the solutions, right? So we would know that x equals negative 2 is a solution, and x equals positive 2 is a solution. Now remember, here we're talking about how the degree matches our number of solutions. In a touch and go, we need to count negative 2 as 2 of our solutions, because we have 2 of these, and then we would need to count positive 2 also as 2 of our solutions, and that is how we get up to 4 total solutions. So touch and go, it's a little bit easier to see how it's a counting irregularity, or how we count solutions. Now when it comes to square roots, if we were given this example, again, they would not tell us, hey, watch out for square roots. So in this situation, we would go to chunking because we have 4 terms here. So we would take out, well, we chunk like this. We would take out an x squared, and then we would factor out a -3. And then we have x minus 2, x squared minus 3 equals 0. Now in this case, it's not so obvious, so we can continue to break this down, but this is like the warm-up that we looked at yesterday, where we had perfect squares here. This 4 gave us a perfect square, so it was a little easier to break down. But we can use that same idea, that difference of squares here, except it doesn't look quite as nice. We have a square root involved. And this is why square roots always come in pairs, because this is the situation that creates a square root in our solution. So there will always be 2 of them. So if we were to sketch this on a graph, just to double check, we would have, it goes through at +2, right here. Then the square root of 3, I've got to get that decimal. The square root of 3 is a little less than 2. Square root of 3 would be like right here, and negative square root of 3 would be like right here. So we could plot those points on our graph. Notice that these square roots are not touch and goes, right? This is not x plus 3, x plus the square root of 3 squared, right? That's on its own. So these are points where we actually cross the axis. We cross, we go up to 6, and we cross again. And this end behavior matches an odd degree with a positive leading coefficient. So here's how square root would show up. Here's how we handle it with our solutions. We have 1, 2, 3 solutions, and here's what it would look like on a graph. Last one, imaginary numbers. Again, when we look at this, we would look to chunk it up. Here. 16 x plus 3 x squared plus 16, whoops, x plus 3 x squared plus 16. Now we say, all right, what makes this 0? And then what makes this 0? This is a little bit harder to see what makes it 0, right? If this were x squared minus 16, we'd go plus and minus 4. It might be helpful to set up a little equation to say, all right, what makes x 0? How can we solve for x so that it is 0? And we all know that we can't have a negative under a square root, so that would just give us plus and minus 4i. You won't have to write this little equation every time. As you get better at them, you'll recognize that a little bit quicker, but that can be really helpful. And this is also why imaginary numbers come in pairs, because anytime they show up, it's in a situation like this where we have an x squared plus something, and to square root it, we would plus and minus both sides. So those imaginary numbers always come in pairs. Now, this graph would look 2, 3, would look something like this if you were to throw it into your y equals. So only one solution, real solution, would show up, but by factoring we can see that imaginary solutions come up as well. Now I have another example here. Why did I put this example together? Oh, yeah, now I remember. Actually, we are going to skip this example. We're doing pretty good. Now, maybe these questions make a little bit more sense now than they did yesterday. So if we look at this one right here, write a polynomial function f of least degree that has a rational coefficient, so real numbers are the coefficients, a leading coefficient of 1, just like we had earlier, and here are the zeros, 2, -4, and square root of 5. So that means when this is all said and done, we need solutions of 2, -4, and then we have to at least have the square root of 5. Now we know, and this is where it's a little bit tricky, because we know that we can't just have a solution that's the square root of 5. Right, that these come in pairs. So we would also need a solution here of -√5. We would get these by x minus 2, x plus 4, x minus √5, and x plus the square root of 5. That's all we would need to write. If we had more time, if we weren't virtual, we would need to FOIL all of these out and all that good stuff, but since we're virtual and since we lost a week earlier, we'll just leave it in this form. Same idea, write a polynomial, leading coefficient of 1, zeros at 2, and 3i. Again, they don't say that positive 3i and negative 3i. That's just something that we are expected to know. So that means when we write our polynomial, we need a -2, we would need a positive 3i, we would need a minus 3i. That's it. Here would be our solution. Last one, a little bit trickier. We have a 0 at 5 and at 1 plus I. So we know when it's all done, we need a solution at 5. And again, we know that we would need 1 plus I as a solution and 1 minus I as a solution. Now, this is where it gets a little bit tricky again. I mean, the 5 is no big deal. Now when we write these two, we always start with x minus, and then we put another set of parentheses, 1 plus I, x minus 1 minus I. So notice that we keep a negative here and here. We keep x minus, that's our default. And where we change the sign is inside of the parentheses right here. All right. Again, hopefully this cleared some things up from yesterday. I mean, my goal yesterday was not to bounce all over the place and have that be frustrating or a really long time, but at the same time, a lot of this stuff is very connected to what we've been talking about. I mean, this is where we put together factoring, we put together finding zeros, we put together graphing, we put together complex numbers. We put together a lot of things that we have talked about really in Algebra 1 and in our class so far. So hopefully this clears it up. Obviously, if you have more questions, then make sure that you let